Okay, we should be live. Just testing a few things, mainly sound. Go live on. Can't avoid Google Studio thing because I need the link to the stream. Link to the stream. Twitter is asking if I want personalized ads. No, I do not. Because that's a code name. I'll spy the hell out of you. Why is the wrong thumbnail? Wrong thumbnail. I forget to add a thumbnail. I must have. God, 1 sec. How do I change it? No, I do have the thumbnail. No, why it's not coming up? It's not coming up. Yeah, whatever. My face, the green, the face recognition is flickering, is it? Ah, no, it's when I look down like this. A crazy delay too. The delay. There is a delay. So we'll come back to Barney Chaos. We didn't forget about the website. We keep updating things. It did stop working for a while recently because this silly what are they called? Certificates have expired, and I thought I have an automated thing running that will renew them, But that, of course, on the judgment day did not work. So that wasn't fun. Took me a while to get it running again. So it's easy to get the certificate and everything, but the deployment on IIS, which I use, so I host everything myself on IIS, is quite straightforward to deploy. But then National Instruments, the API that I use to run this, the deployment of certificates over there is a bit more complicated, to say the least. But now it's working again. I have to remember when I test this site, I need to well, first I'll need to make a unit test for it. But then I had something running that will just ping the site, see if it's online or not. But that's very basic. You can now hear my GPU is going. Yeah, this is probably the heaviest app that I have at the moment. Currently, you can see on the what is that bottom left. Whatever I have running. Is it playing or what? Yeah, there's that delay. Keeps sending. It's a bug that was there for a while. It become worse. Well, yeah, it will play eventually. Yeah, if I close this tool usage, CPU drops a bit. Yeah, GPU stay the same, which is odd. But yeah, close those for now. So yeah, eventually a lot of the tools that we create at the moment will go online. Hopefully there will be some sort of tool that will teach sign language. No, you can't wait for that one, can you? Let me just check. You other things. Interesting, just an observation. When I live stream, I don't get many views, but interestingly, people do watch. I get a increase in watch time for other videos, which is interesting. I think the algorithm really likes live streams. Let me know if you'd like to see the YouTube analytics or something. I should make a video on that. So what we were doing is right. So another side note. We have the GitHub Copilot trial period running out tomorrow. So by the end of the today, we essentially have to make a decision if we keep using it, which means paying for it, or just drop it. So I kind of briefly started comparing it to Tabnine, which is probably a more evolved version, as opposed to Captain Stack, which will just find. So this is testing Captain Stack. What it does is, for example, if you just type in a find basic chart example. Once you hit a full stop, so here it says it found 12 results. It's actually 14. I don't know why it says only 12. Then you can scroll through them, and those are direct. So you have the source, which is a big difference to ChatGPT, which doesn't give you any sources. So it's just essentially a copy of this Stack Overflow entrance. So it's essentially just a fancy search for it, and it will bring the code directly into your directly into Visual Studio Code. So it can be quite handy. So for example, this one has some example numbers and plots bars. So you can, what did I do? Some crime time. Where's the data from? Plot show. No, it's getting the data. There's probably a more interesting one. Generate dummy data, right? Once you run it, it's actually running. I don't know. I think that I don't understand in Python is if you can run a multiple scripts at the same time. And you would think that's possible. Anyway, so essentially we now that we work, we still have Copilot going. And it's not clear now which one. Oops. Right, so this is actually that's interesting. I think they're now getting Tabnine. So supposedly Tabnine it's free, Tabnine is free, but the Pro version will have advanced completion. It doesn't actually say what it is. There's a free trial for 14 days, and then it's actually more expensive than Copilot. So what's completing? What's doing the? Oh, it's not just the same code as we had before. Yeah, it's hallucinating something. Yeah, so when three of them working, well, I know it's not into data frame. I already had that. That's just giving us the same thing. Probably have to try them in separate files. It's funny how the Copilot you can disable everywhere or for specific language, but why not disable it for no option to disable it for a specific file? That could be handy. We want ChatGPT. We want to know in Visual Studio. You open another You can open another iteration of it. Tabnine. Where's that file at? It's in the same folder, testing. Right, I'll just open another iteration. Right, so that's what as here we're testing Tabnine. We just wrote find basic chart example. It gave us the source, and yeah, and this code, which I assume is a copy paste from Stack Overflow, as it says here. It will actually run, so that's all good. So this is how it works. It's pretty straightforward. Is it running? Yep, 10 stack. It is running. It's finding find create web page, and it found loading 3 results, even though I'm pretty sure it had more there. It's using this cherry pie. Yeah, that doesn't look right. And then Tabnine will complete lines of code. Oops. So for example, if I accept that, yeah, is that completion by Tabnine or Copilot? Just disable Copilot. That must be in build. It's not giving any suggestions. I don't know, is Tabnine working? Choose the type of code. Yes, data. And Pro will like similar to ChatGPT will complete the whole function or whatever it is, multiple lines. So if I is being completed by wait, I have to remember this VSC is running this script. So I have to keep that running as is. Then this one yeah, the Copilot is turned off. Just giving me the same. Engine start, engine block. And is it giving any? It's not great, is it? If this file is run as a script, this file run as a script, run it. It's not a great comment, is it? Yes, I expect Copilot was giving a bit slightly better comments. So we had this code here. So SL finger spelling recognition with TensorFlow. It takes some time to run. We'll run all of it with Python 3.11. It was working okay. It's what we have in the data. Yeah, I was adding some. This is what the data, the raw data looks like. And how come I don't? Right. There was some explanations of the code. I was using this line to say here. Right. So that's what Tabnine. Oh, now it changed. Huh. It's weird. It takes this return list of tokens. Doesn't sound right. Anyway, we'll have to do more on this code. Customer aid training variable, transformer, decoder layers, combination of 3 multi-head attention layers. Or whatever. So let's do this first. There's a really good resource for learning machine learning. So we'll try the image project because it's easier. Interestingly, that suppose we can run this one. It's the model size of around 500 kilobytes, and this one around 5 megabytes. Yeah, we can do megabytes. We can. Why am I using the camera? Well, I use the OBS virtual. This is browser fail. Doesn't let me choose a different camera. Am I using the second? Because I have 2 of them in front of me. This is one, and the other one is doing the face and hand recognition. Won't let me. Yeah, this won't be a problem. Just turn that script for a sec. Turn that script. Control C. Right. We use this. This call this class me a hold to record. Yeah, got maybe more turning head. So there's 156 images. A class 2, let's do phone. Now here we have advanced option as well. Let's stick to about 10 epochs, see how we go. That should be plenty if the data is clean. Let's do a phone. We'll turn it back and forth. It's phone and hand, obviously. Enough 200 images. 200 images got font. Well, it will all have hand in it. Let's add another class. Be do a pen. Do a 143 images. Do a epochs. This is a nice explanation of each. Batch is a set of samples used in one iteration of training. For example, let's say that you have 80 images and you choose a batch size of 16. This means the data will be split into 5 batches. Size 16 sounds legit. One epoch means that every sample in the training dataset has been fed through the training model. Yeah, you will see it in a sec. Yeah, tweaking this now. Okay. We'll open this under the hood. We'll train the model, shouldn't take too long. And see its performance over here. Yeah, so it's saturating after well, 2 epochs or so. So it's an easy data set. And here you can see how it performs. So here it's recognizing. I forgot to add the name. Should be pen. Doesn't matter. So this one getting confused between phone and pen. I don't know why. Getting confused between the phone and pen. I don't know why. So this has phone, me, doing well on that one, me, and saying 30 and 20 whatever percent pen. So it's getting confused there. Calculate accuracy per class. Accuracy per class is calculated using the test samples. Check out the vocab section to learn more about test samples. Test samples are never used to train the model. So after the model has been trained, the training samples check how well the training is performed. Test samples, right? So test samples, what's going through the camera now. Sorry for that. Just doing me. I'll just retrain it. Because yeah, if you do this, it thinks this is a phone. How about Sunny's? Yeah, it's getting confused. It's sometimes thinking it's a phone as well. Sorry for that. Train it on. It's 5.5 where headphones, it will still recognize me. Saving. It's thinking there's a phone in the image as well. So let's just add class quickly. Do a camera. Two 277 images. I called them headphones. Now, obviously, for phone and pen, yeah, just train it again. We can reduce the number of epochs to like about 5 because it's saturating already. Let's do 4. Train again. And calculate the confusion matrix. You can see here as well. Doesn't actually fit to the screen. So this, yeah, means very good performance. So how do we turn it into a supervised network? Yeah, moving away, it's getting all confused. And this thing as well, it's thinking that's a phone, even though it's obviously not a phone. So I don't know what's up with that. So its performance is, well, it says it's good, but it's not really. Loss. So yes, you can add more images. So we almost 300 batch size. Probably increase the batch size now. Learning rate. Right. So obviously, right model again. No, it didn't train. Did it? Changed them. Oops. Oh, come on. You would think this is a small change. It's getting confused between the headphones and the phone, and forgot about the pen. Now, if it has me in the background, it's probably still don't need that many epochs. You could still stick to say 10. This number. Try it again. 10 epochs. Oh, come on. Why is it deleting the whole thing? Can't enter a number properly. Right. It's obviously doing it locally. It's using CPU or GPU. 2164. It was using CPU. That didn't work. So it didn't train. It's thinking I'm a phone. Try this again for a sec. Give it to 10. And that actually is a bit better, is it? Still not recognizing the pen. So what if we train the pen? What was the pen? Just add more with me in the frame. So it could be with me or without me. Let's just try this quickly. Me, pen. It's funny. The OBS. It's thinking it's can crop it. And why is it? Flip it and crop it. Phone gives. It can't recognize me anymore. So just a different background and it can't recognize. Yeah, now it's all so the background is important. Can you add stable class, download sample, save sample? No, delete class. Yeah, I didn't train it correctly, but that will do. Just trying to train it quickly again. Right. Oh, come on. The interface is funny. One, right, reverts to default camera. Let's see where the learning rate starts taking effect. This should go up to 1. Right. 1.5. Seems like this is the threshold number for whatever reason. Hmm. That's weird. Yeah. Anyway, you get the gist, and you can save this model. Just export it quickly as a JavaScript. Use the code snippet on GitHub. Download. Keras, OpenCV, Keras, Android. Alright, so TensorFlow Lite can do Android. That's good to know. It's fine. It says converts your model to Keras H5 model. Not the conversion happens in the cloud, but your training data is not being uploaded. Only your trained model. JavaScript, TensorFlow, JS. Right. Can I host this myself? It's an API. Loop, update, webcam, frame, prediction, JavaScript. We'll download this in a zip file. It's 2 MB zip file. We'll close that. Yes, anyway, you get the underfit. A model is underfit when it classifies poorly because the model hasn't captured the complexity of the training samples. Overfit, the model is overfit when it learns to classify the training samples so closely that it fails to make correct classification on the test samples. So is this accuracy? Turn it back on for a sec. Percentage. It's thinking that's a pen. It's thinking my hand is a pen. Why not a phone or headphones? Accuracy is the percentage of classification that a model gets right during training. If your model classifies 70 samples right out of 100, but how this accuracy, how does it know? If the model prediction is perfect, the accuracy is 1. How is the accuracy is lower than 1? But this is not accurate. I don't get it. Don't get it. We had a video. Can I do this? Can I do that? Watch this for a sec.
Instead. So I'm going to try and get the same number of images as before, and that's important because if you have too many of one class, statistically speaking, the machine learning will think that that's more likely to appear just naturally, so it might learn just to predict that object all the time, and of course when it's training, it would be right 90% of the time. So it's important to have roughly the same number of examples for your training. Let's give it a more meaningful name. So the first thing I'm going to call Jason, and the second thing I'm going to call Bottle, as shown. Okay, so we now can click on webcam, enable access to our webcam if it's the first time using this site, and if you allow access, you should then see your webcam come into view. Now, if you've got multiple webcams, you click on the drop down to select the right one. And now we're going to hold to record some images of the thing of interest. Now, this one is Jason, so that's me. And of course, you're going to record your own things over there, so feel free to change your names as needed. And I'm going to try and get some sample images of myself right here. Note, I move my head around to get some variation as well. I've got about 43 images, and that's great. That should be enough. We now go to bottle, click on webcam, and here I'm going to try and recognize this bottle instead. So I'm going to try and get the same number of images as before, and that's important because if you have too many of one class, statistically speaking, the machine learning will think that that's more likely to appear just naturally, so it might learn just to predict that object all the time, and of course when it's training, it would be right 90% of the time. So it's important to have roughly the same number of examples for your training data. Let's try and do the same thing here with the bottle nice and close to the webcam, and get roughly the same number, 40-something images. 44, that's close enough. Now, let's go ahead and train our model. And what's happening now is that live in the browser, TensorFlow.js is going to retrain the model so it can distinguish between these two different object types. And you can see it's already finished. It happened pretty fast. And you now got a preview on the right-hand side of it in action. Now you can see right now that it says Jason with 100% confidence, which is technically correct. And if I bring the bottle into view, it switches to bottle with 100% confidence, which is also now correct. Jason, bottle, Jason, bottle. And look how fast that is. It works in real time. And this is very usable for a prototype, for example. Now, if this is good enough for your needs, you can actually click on export model at the top here, click on download, and then click on this button here to download the model files. This will contain things like a model.json and some binary files you can host on your website to then use in any way you wish. And of course, we're giving you some example code down below here that you can use to get started. But don't worry about that for now. We'll be teaching you all about how to code later on. So for now, let's go back and focus on training data. Now, I just trained a system that recognizes the difference between me and a bottle. And that's great, but let's try other bottles to see if it manages to recognize those too. Let's try this one. Pretty good, not too bad. It seems to be recognizing that shape is important here. And let's just try one with a different color as well. And again, it gets that that is actually a similar thing. Now this is great. However, if I bring into view this kind of jar-like object, it's not quite as sure, but it gets to the 90s, which is pretty confident. So we might want to train the system to be better at recognizing jars, for example. So in order to do that, we can add another class on the left here, maybe call it jar, like so. And now we can add training data for that. So let's go ahead and get roughly 45 images of this jar here. Let's open that up like so. And get roughly the same number of images. 44 is good enough. Hit on retrain to train the model once again, between 3 objects this time, not 2. And now you can see we've got JSON, bottle, or jar showing. And if I show it the jar, it's now 100% confident that that is a jar, which is correct. And let's go ahead and test the bottles again. It's always good to retest things. The bottle.
This is interesting. So it's recognizing the bottle perfectly well. And then it's confusing me for a bottle sometimes. What? Why? Why am I a bottle? It's recognizing my hands as a bottle. Yeah, it's getting confused. And interesting enough, why is it getting confused with me? But then I realized that before, when I trained it, I didn't have my headphones on. So now it does 100% me. So that's interesting. And now it's getting about 50-50 me, bottle, me, what's going on. Can just try and just train it with my headphones on as well. Just retrain it quickly. Yes, it's probably too many samples, but we can deal with that. Where was the beat on? Right, and now it's doing better. So 100% bottle. Me. And it should recognize me without headphones as well. So that's okay. And if you, that's recognizing this cup as a bottle. So pretty much anything that comes into the screen, it will recognize it as bottle, which is essentially not a bottle detection, but detecting an object in the screen.
Was 100% confident there, and our Coca-Cola bottle, 100% confident. And let's bring that green one again back into view. And oh, what happened here? It actually thinks it's a jar. And why might that be? Well, looking at these two objects, you can see that they're both green, or a lot of green contained within them, right? So what's happened is that it thinks that a jar is just some green object, whereas a bottle is this kind of bottle-shaped object, right? So in order to get around this, you're going to have to add more training data to your examples to improve the accuracy, and so it knows that this is in fact a jar versus a bottle. So what we're going to do here, well, for this bottle over here, we're going to go back to the bottle training data, click on webcam, and we're going to add some examples of this bottle to the scene so that we know that this is a green bottle, okay? So let's go ahead, put that in view, and click hold to record. And there we go, we've got about 84 images now. Now, because I've got 84 images of bottle, I need to go and get some more training data for my other classes as well. So let's go back to JSON. Oh, let's move the bottle out of view because that'd be contaminating my data. I'm going to click train model and get some more of me. Oh, sorry, not train model, click hold to record. So now I'm going to click hold to record to get some more training data of me. So roughly 77 there, let's get a bit more. 80, okay, 90, okay, that's close enough to 84, that should be fine. And now let's do the same thing for jar as well. So open up the webcam for jar and put this back into view here. And let's get some variation of the jar and get roughly, 93, okay, that should be close enough. So now if I click on train model here, we're gonna have a lot more training data. It might take a bit more time, but we should now get a more reliable output model that can distinguish these things. So here we go, JSON, 100% correct. Bottle number 1, close enough to 100, that's good. Bottle number 2, straight in there, 100, very good. Bottle number 3, which was the one that was causing us problems before, 100%, beautiful. And now if we try the jar, hopefully it still remembers that this thing over here is a jar. And as you can see, we've now trained a much more robust model. So go ahead and explore yourself with objects in your room to see what you can recognize and what causes problems and what doesn't. As you experienced, the machine learning model you created was as good as the data that you presented to it. The more data you use, the better it can be at generalizing, just like the image shows on this slide. All of these objects are bottles, but if you only use one type in training, the model could struggle to detect the other types in the future. Instead of learning that color was the distinguishing feature, it might learn that shape was more important, leading to a more robust system. As you saw, in this use case where images were the input, you do not have control over what features it decides are important, as it will decide by itself based on the data presented what distinguishing features provide the best data separation. And by providing varied inputs, it has less chance of choosing wrong features. Be careful though, in all the images I just showed you, I use my hand to hold the object. In this case, it could learn that the hand is the thing to recognize and not the object itself. Technically speaking, it would be correct as my hand existed in every single image that we showed it, but as a human, you know that this was not the intended outcome. Continue to explore using Teachablemachine to see what edge cases you can find that lead issues for the object you're trying to recognize. Maybe try with other objects too if they're similar and see how that goes.
All right, it's probably did recognize my hand instead of the bottle. My hand is holding the bottle because every time I show the hand, it's telling there's a bottle. And if I just did bottle with no hand, it's actually not recognizing the bottle. So yes, big lesson there. It's just you're thinking it's learning one thing, but it's actually learning a whole different thing. So yeah, now it's saying everything is a bottle in this image. Yeah, now with like just a different background and stuff, and it's yeah, off the charts. I think now it will just keep saying everything is a bottle. Right. So it's getting confused by the logo. That's not sure. It's like 50-50. You can make it. Yeah, it's not sure if I'm a bottle or me. So yeah, just get back to we are done with this. Let's turn image recognition back on. Be using the Ava camera. Yeah, that's right. That's the one that has hand recognition in it as well. It's this circle. I don't know if that anti-aliasing actually does something or not. Right. Without. And let's also make this should be the thickness of the line for, was it -1? Circle. Right, that's the center and radius. Center and radius. And there's a shift of -1. I don't know why. Can we have the radius double? Right, those are just bigger. Yeah, we double the radius. Yeah, this window is funny because if I hold on to it or minimize it, it stops working. Right, and in the competition stuff, let's put it on another screen because we have it in OBS at the bottom. Right, in the competition, they label um, every finger in a different color. So this is someone signing. I don't know what letter. What letter is that? I have to check the dictionary. So they're going like this, and that's what we train a model on. So we also have the body pose. I don't know why. Like, how is it actually being used? Create feature columns, some pre-processing data set into DF records. 128 frames. Load the pre-processed data, right? So yeah, and we only do that once. Make sure there was this bit of code that we want to make sure it's not actually doing it again, because it took half an hour the first time we were running it. I lost that bit. Right, this one, if pre-process directory exists, we would not be doing all this again. This bit took a half an hour the first time we run it. Essentially turning the data from the Parquet files into TensorFlow dataset. The 68 TF record files. So we have that character to prediction. And the point of it, I'll just scroll quickly. We're using a transformer model used for speech recognition. But that's not doing a great job. So probably have to either use a different model or see what else we can do with it. Because the performance of this is really, really bad. Oh, did get the errors in there? Yeah, I was looking at that M before. It seems like something was cut out. Transformer model. Yeah, this code was generated by Copilot. Sorry, the code is from the competition demo. The annotations were generated by Copilot. I don't know why we having. Where's that line? Seems like something was cut. We can select this and go explain. know why it's writing so much. The code above is implementation of the training model. The models train a model fit. Self amp line 8 in the beginning. What? I can't find it. There's no amp. What? Model. There's no such thing. What the? Right, this one executed okay. Token embedding. Does seem like something is. There's nothing to fix. There's no errors. Code above defines two custom layers for the model. The first, the token layers, 3 parameters num. Yeah. This self emb. What seem to be a problem there? What was? Embedding layer. This and below. See if that's all. That seems like a callback function. While we're training again, we already trained before. Well, this will take some time, but it's working now. It's just by mistake, like cut out the half of the line, code line. Yeah, this one getting confused between the hands, saying left is right, right is left. No, it's saying both are left when they're both red. So I don't know what's up. What's up with that? Yeah, the loss is kind of saturated already anyway. Or is it? No, it's still going down. The loss, but why is it 13 epochs? Do we need 13 epochs? To put this into ChatGPT just because it has every text to speech works much better. Get rid of that. It's like this.
GitHub Copilot. The code above defines two custom layers for the model. The first layer is called token embedding and is used to tokenize the input. The second layer is called landmark embedding and is used to embed the landmarks. The token embedding layer takes three parameters: number underscore vocab, max len, and number underscore hit. Number underscore vocab is the number of vocabulary tokens, max len is the maximum sequence length, and number underscore hit is the hidden dimension of the embedding outputs. The layer consists of an embedding layer and a positional encoding layer. The embedding layer is defined using the tf.keras.layers embedding function. The positional encoding layer is defined using the layers embedding function. The call function of the layer takes the input x and returns the sum of the embedding and positional encoding. The landmark embedding layer takes two parameters, number underscore hit and max len. Number underscore hit is the hidden dimension of the convolutional outputs, and max len is the maximum sequence length. The layer consists of three convolutional layers and a positional encoding layer. The convolutional layers are defined using the tf.keras.layers (SONV1D) function. The positional encoding layer is defined using the layers embedding function. The call function of the layer takes the input x and returns the output of the third convolutional layer. These custom layers are used in the model to tokenize the input and embed the landmarks. The token embedding layer is used to tokenize the input sequence, and the landmark embedding layer is used to embed the landmarks. The output of these layers is then passed to the rest of the model for further processing. Possible ways to improve the code with respect to readability and performance include adding comments to explain the purpose of each line of code, using descriptive variable names, and optimizing the hyperparameters of the model. Additionally, it may be helpful to split the code into smaller functions or classes to improve readability and maintainability.
Right, well, I didn't ask.
Version. Comments are added to explain the purpose.
Didn't ask to. I thought it was just explain it, but I had to specify it, didn't I?
Purpose of each line of code. The variable names are more descriptive to convey their meaning. The hyperparameters of the model, number underscore vocab, max len, number underscore hit, are defined as variables for easy modification. Additionally, the code is organized into a class structure for each custom layer, which improves readability and maintainability. The layers are instantiated and used in a usage example at the bottom for demonstration purposes. Remember to adjust the hyperparameters according to your specific requirements and the nature of your dataset. Regenerate response. Free research preview. ChatGPT may produce inaccurate information about people, places, or facts.
Yeah, that's right. Right. The good thing about it is that you can. Where's the edit? You can edit the. Yeah, how about make it simpler as well?
This code has two custom layers for a model. The first layer is called token embedding and it tokenizes the input. The second layer is called landmark embedding and it embeds landmarks. The token embedding layer has three parameters, number underscore vocab, max len, and number underscore hit. Number underscore vocab is the number of vocabulary tokens, max len is the maximum sequence length, and number underscore hit is the hidden dimension of the embedding outputs. The layer includes an embedding layer and a positional encoding layer. The call function of the layer takes the input x and returns the sum of the embedded.
Yet the loss doesn't seem to change anymore, and still going for another 12 epochs. So it just finished the first one, and it's making all these mistakes. So that's what the target sentence is. This is what someone spelled out in sign language, and this is what the model is predicting. As you can tell, it's way off. Right, and this is now the loss keeps going down. That must be a good thing. Sorry, all this stuff. Whoop. I can't move that. I'm still can't move. Doesn't matter. Where's the thing? Whoop. And the loss keeps going down, which is good. Supposed to be good. That's what we had here. Loss is measured for evaluating how well the model has learned to predict the right classification for the given set of samples. If the most predictions are perfect, the loss is 0. Otherwise, the loss is greater than 0. To get an intuitive sense of what this measures, imagine you have two models A and B. Model A predicts the right classification for a sample but is only 60% confident of that prediction. Model B also predicts the right classification for the same sample but is 90% confident of that prediction. Both models have the same accuracy, but model B has a lower loss value. So it's meant to be translated into false negatives and false positives, whereas this will be your hit rate, so your hits and misses. It's funny, there's something not right about that one, but anyway, I have to do it again sometime. It's called the mentioned loss. I want the ChatGPT to write the sentence paragraph on in terms of false alarm.
In the context of machine learning and neural networks, loss refers to a measure of how well a model's predictions match the actual expected values. It quantifies the difference between the predicted output of the model and the true output. The goal of training a machine learning model is to minimize this loss or error. Loss functions are mathematical functions that calculate the error between predicted and true values. They take the predicted output and the true output as inputs and produce a single scalar value, which represents the magnitude of the error. The choice of loss function depends on the specific task and the type of data being used. During the training process, the model's parameters are adjusted iteratively to minimize the loss. This is done through optimization algorithms that update the model's parameters in a way that gradually reduces the loss. By minimizing the loss, the model improves its ability to make accurate predictions. Different types of machine learning problems, such as classification, regression, or sequence generation, may require different loss functions. Some common loss functions include mean squared error, MSE, categorical cross-entropy, binary cross-entropy, and softmax cross-entropy. The selection of an appropriate loss function depends on the problem at hand and the nature of the data being used.
Loss in terms of false, false negatives.
Loss in terms of false positives and false negatives is typically associated with binary classification problems. In such problems, the model's predictions are categorized into two classes, positive and negative. A false positive occurs when the model incorrectly predicts a positive class when the true class is negative. In other words, the model mistakenly identifies something as belonging to the positive class when it should have been classified as negative. A false negative, on the other hand, happens when the model incorrectly predicts a negative class when the true class is positive. It means that the model fails to identify something as belonging to the positive class when it should have been classified as such. The loss function in this context aims to capture the cost or penalty associated with these misclassifications. It quantifies the overall error or discrepancy between the predicted and true classes, considering both false positives and false negatives. Different loss functions can be used to address this. One common loss function for binary classification is the binary cross-entropy loss. It measures the dissimilarity between the predicted probabilities and the true labels. By minimizing the binary cross-entropy loss, the model aims to reduce the number of false positives and false negatives. Ultimately, the choice of loss function depends on the specific problem, the desired trade-off between false positives and false negatives, and the nature of the data being used.
So in this case, we actually have a very specific way of measuring results. Yeah, so we want it to go lower. Seems like training loss can go lower, but then in the validation, why do we split 80-20? Can we do a different split or something? That's just that won't make much difference, would it? Yeah, and it's already around 0.5, so when it goes just below point, this means yeah, that's where it stops. Is the number of epochs defined to begin with? No. How do we? So it somehow automatically decides optimize the learning rate. This data set. It's learning rate. Just the learning rate in what we're doing before. A 0.001. This has another 0 in it, so why? Okay, we just let it run. It's already 14 minutes through. I'm using 100% CPU. What? Why? Why do I use GPU as well? CPU. Just close inside this. Just close this one for a bit. I limit the CPU use or something? Using all of my Oh, right now it's better. Yeah, I had to close. Yeah, obviously, while training a model is a good idea to close any other major things. It's 18 minutes. It's a 7th epoch. It's getting down to 0.5 on the loss scale.
Loss in terms of false positives and false negatives is typically associated with binary classification problems. In such problems, the model's predictions are categorized into two classes, positive and negative. A false positive occurs when the model incorrectly predicts a positive class when the true class is negative. In other words, the model mistakenly identifies something as belonging to the positive class when it should have been classified as negative. A false negative, on the other hand, happens when the model incorrectly predicts a negative class when the true class is positive. It means that the model fails to identify something as belonging to the positive class when it should have been classified as such. The loss function in this context aims to capture the cost or penalty associated with these misclassifications. It quantifies the overall error or discrepancy between the predicted and true classes, considering both false positives and false negatives. Different loss functions can be used to address this. One common loss function for binary classification is the binary cross-entropy loss. It measures the dissimilarity between the predicted probabilities and the true labels. By minimizing the binary cross-entropy loss, the model aims to reduce the number of false positives and false negatives. Ultimately, the choice of loss function depends on the specific problem, the desired trade-off between false positives and false negatives, and the nature of the data being used.
Okay, so we only have 40 minutes. Will it finish in it's been going 20 minutes and 7th epoch. It's still going down. Alive. Still alive. And that's what we got last time. We're not expecting anything different, so I don't know why we're doing it again. Once training is done, is there an option to not train again unless parameters have changed? Carefully convert prediction indicates. Assume val loss is validation.
Training loss and validation loss are two types of loss values that are commonly used to evaluate the performance of a machine learning model during the training process. Training loss refers to the loss calculated on the training data during each iteration or epoch of the training process. It measures how well the model is fitting the training data. The training loss is calculated by applying the chosen loss function to the model's predictions and the true labels from the training set. The training loss is calculated by applying the chosen loss function to the model's predictions and the true labels from the training set. The goal of training is to minimize this loss by updating the model's parameters through optimization algorithms. Validation loss, on the other hand, is the loss calculated on a separate validation set that is not used for training. This validation set contains data that the model has not seen during training, and it serves as an independent evaluation of the model's generalization performance. The validation loss provides an estimate of how well the model is performing on unseen data. During the training process, the model's performance on the training data is monitored through the training loss. The model's parameters are adjusted based on this loss to improve its fit to the training data. However, it's crucial to assess the model's performance on unseen data to ensure that it is not overfitting, i.e., becoming too specialized to the training data and performing poorly on new examples. This is where the validation loss comes into play. By monitoring the validation loss, we can assess the model's generalization capability and determine if it is overfitting or underfitting the data. Ideally, we want the training loss and validation loss to decrease together during the training process. If the training loss continues to decrease while the validation loss starts to increase or remains high, it could indicate overfitting. In such cases, additional measures like regularization techniques or adjusting the model's architecture may be necessary to improve generalization performance. Ideally, we want the training loss and validation loss to decrease together during the training process. If the training loss continues to decrease while the validation loss starts to increase or remains high, it could indicate overfitting. In such cases, additional measures like regularization techniques or adjusting the model's architecture may be necessary to improve generalization performance.
Right, so that's what we'll have to look into next. Probably another day. Just say bye for now, and we'll keep going. We'll probably stop this one because it's been going for 24 minutes and we're not expecting any different results to this. One thing that we do want to change is we want to run the TensorFlow on the GPU. That would be handy. Get CPU 100% again. What? Estimated time of arrival is it? That's 2 minutes for this epoch. This number too small. Maybe that's why it takes forever.
In the given code snippet, an optimizer is defined using the Atom optimizer from the Keras library. The learning rate for the optimizer is set to 0.0001, which has been customized from the original learning rate used in a Keras tutorial to better suit the specific dataset being worked with. Optimizers play a crucial role in training neural network models. They determine how the model's parameters are updated during the training process in order to minimize the loss and improve the model's performance. The Atom optimizer is a popular choice that combines the benefits of two other optimization methods, AdaGrad and RMSProp. The learning rate is a hyperparameter that controls the step size at which the optimizer adjusts the model's parameters. The learning rate is a hyperparameter that controls the step size at which the optimizer adjusts the model's parameters. It determines how quickly or slowly the optimizer converges towards the optimal solution. A smaller learning rate can lead to slower convergence but can be more precise, while a larger learning rate can lead to faster convergence but may result in overshooting the optimal solution. In this code, the learning rate is set to 0.0001, which is a relatively small value. This suggests that the model is being trained with a fine-grained adjustment of the parameters, potentially aiming for more precise optimization. The choice of the learning rate depends on the dataset, model architecture, and other factors, and it often requires experimentation and tuning to find the optimal value for a specific task.
Hey, can we save that? Just copy to clipboard, put it in right with my, let's stop it for a sec. This number doesn't have to be that small, I reckon. But we are just learning, so just increase it tenfold and see what happens.
This suggests that the model is being trained with a fine-grained adjustment of the parameters, potentially aiming for more precise optimization. The choice of the learning rate depends on the dataset, model architecture, and other factors, and it often requires experimentation and tuning to find the optimal value for a specific task.
How to prevent CPU? Do voice typing. Win H. Prevent CPU going to 100% and ideally use GPU. Yeah, I'm pretty sure it's available.
Ensure GPU availability. Make sure you have a compatible GPU installed on your system and the necessary drivers and libraries, such as CUDA and CUDNN, are properly installed. GPU acceleration with libraries. Utilize GPU-accelerated libraries for computations. Many deep learning frameworks, such as TensorFlow and PyTorch, have GPU support built in. Ensure that you have installed the GPU version of the framework and properly configured it to utilize the GPU. Set device placement. In your code, explicitly set the device placement to utilize the GPU. This ensures that computations are performed on the GPU instead of the CPU. In TensorFlow, you can use tf.device/GPU0 or tf.device/device GPU0 to specify GPU device placement for operations. Batch processing. Perform computations in batches rather than individual samples. Batch processing allows the GPU to parallelize computations and perform them more efficiently. This can help reduce CPU usage and improve overall performance. Monitor and adjust batch size. Monitor the memory usage of the GPU and adjust the batch size accordingly. If the batch size is too large, it may exceed the available GPU memory and lead to out-of-memory errors. Decreasing the batch size can alleviate this issue and improve GPU utilization. Data preprocessing on CPU. If your data preprocessing steps are performed using CPU-intensive operations, such as loading and preprocessing data from disk, consider parallelizing or optimizing those operations to reduce CPU load and minimize the impact on overall system performance. Consider distributed computing. If your workload is particularly resource intensive, you can consider distributing the computations across multiple GPUs or utilizing cloud-based services that provide GPU instances for high-performance computing. Remember that the effectiveness of GPU utilization depends on the specific task, model architecture, and available resources. It's important to profile and monitor the system to ensure efficient resource utilization and avoid bottlenecks. Regenerate response. Free research preview. ChatGPT may produce inaccurate information about people, places, or facts. Remember that the effectiveness of GPU utilization depends on the specific task, model architecture, and available resources. It's important to profile and monitor the system to ensure efficient resource utilization and avoid bottlenecks.
So it will be, what is it, 4 minutes per epoch or for the whole thing? Does it set to stop when the evaluation loss function starts increasing? So when the divergence it stops dropping because there's no epoch by the batch of outputs every the predictions after every 4 epochs. Something is running every buzzer implementation of the display output class. Display class is subclass of Keras callback class. Displayed out so used callback model feed function. No, history. Yes, there's it is set history. Epochs is customized from original Keras tutorial to suit this data set. Can you save that model instead of doing it again? And then we will create another model. So if we're training trans after training the transformer model, can we save it and train another one instead of training again and again?
You can save the trained model and load it later for further use, instead of training it again from scratch. This can be beneficial in several scenarios, such as reusing trained models. If you have trained a transformer model on a specific task and dataset, you can save the trained model and reuse it later without the need to train it again. This is particularly useful when you want to apply the model to new data or deploy it in a production environment. Transfer learning. Saved transformer models can serve as a starting point for transfer learning. Transfer learning involves taking a pre-trained model and fine-tuning it on a different but related task or dataset. By loading a pre-trained transformer model, you can leverage the knowledge and representations learned from the previous training and adapt them to a new task with less training time and resources. Experimentation. Saving the trained model allows you to compare and evaluate different model architectures, hyperparameters, or training strategies without retraining from scratch each time. You can load the saved model, make the desired modifications, and continue training or evaluate its performance on new data. To save a trained transformer model, most deep learning frameworks provide functionalities to save the model's architecture, weights, and optimizer state. The saved model can be stored as a file or in a serialized format, such as HDF5 or TensorFlow's saved model format. Once the model is saved, you can load it using the corresponding function provided by the framework and continue training, perform inference, or fine-tune the model as required. It's important to note that when saving and loading models, ensure compatibility between the framework versions, model architectures, and any custom layers or components used in the transformer model to avoid.
Wait, we already saved this one, didn't we? So we are currently running it again. We have this, then after running the model, training the model, we run this, display this plot. Then we have another model. Create a TF file. The code below is used to save the model to a file. Also have to file, so it can be loaded, used, the model saved in file. Well, H5. Can we stop this? We'll do that. We save, and now we want to use it because we're already have it. Where is it? Pre-process. Yeah, we have 20 megabyte from yesterday. Yeah, that's what we did it already. If more code on the model H5. Yeah, we want to use it. Yeah, I'll continue this probably tomorrow. We have this one twice. Don't need it. Now the question, if we have this file already, what's that? Doesn't look right. Anyway, I'll just continue. This we have to figure out how to use the model, not save it. Then we'll look at how to make another model, another layer or model. Yeah, probably model to improve on this one. So this one gets us to like 50% there. So then we need to do the rest ourselves. So see you next time. Bye.